All right, welcome back to the next lecture. This lecture is part one of maximization and minimization, as well as gradient descent. So I'm a Professor Wu. We'll get started. So today we're going to review the concept of maximization and minimization, and the notation you want to pay attention to is this one. This notation is saying that you want to find the x for the function f of x such that you want to find x such that this function is maximized. Okay, so you see over here is a function, so the maximum is right here, and it's saying that what is this x, which we tend to call it x star. X star is the location of x where the function is maximized. Conversely, this notation is saying that we're trying to find the x where the function f is minimized. So function that looks something like this, you can see that the minimum, therefore you're trying to find this x location very specifically. Now, remember, very often in functions, we're trying to push something higher or lower, right? Like our cancer rate. We want to push the cancel rate as low as possible. So you can see that minimization is you're trying to find the input to push it. You're trying to find the state you're at such that your cancel rate is the lowest. For example, okay. So finding the minimum or maximum. Well, we worked previously about on the derivatives, right? And I emphasized that derivative basically tells us if the function is going up or down at a certain point. So over here, the derivative at 2.9 is going to be positive because it's the function is going up as x increases. Over here, instead, right, the derivative is going to be negative because the function is going down as x increases. Okay, so that's a key. So, well, if that's the case, there's a very special characterization of the maximum or the minimum point, because at this point the function is neither going up or down. Therefore, the derivative at the maximum point or the minimum point must be zero. Okay, so for this simple equation, which looks like this, if we take the derivative of this equation, it will be 2x minus 4. 2x minus 4. And what we're saying is that the derivative at the maximum must equal to zero. So if we put a zero here, this means if then we end up with this equation. So this means that we know exactly what x star is, the optimal location, because only 2 will solve this problem. So if we plug x equals to 2, notice how we'll get a 0. This implies that the minimum location is indeed 2. So if we want to find a maximum and minimum for really simple equations, we just have to take the derivative. And then once we take the derivative and set it to 0, we find the optimal solution. Of course, life is not so simple. We're going to be working on much more complicated equations and therefore we can't just take the derivative and set it to 0. However, in the most ideal case, right, that this would be the best way to find the minimum. And this right here is called a closed form solution. The closed form solution. Okay. Okay. So what happens? So for these simple problems, great. What happens if we have something that looks kind of complicated like this? Now we got to take the derivative of this and set w, the derivative, to 0. And you can't necessarily solve for w because this is a really complicated equation. So for cases like this, how do you essentially find the minimum, right? So that's what we're learning. Very often in machine learning, what's happening is we model the situation with a function. We find a model. Once we find a model, what we want to find the the point, the input into the model that give us some kind of optimal outcome. So maximization could be like earning. Like, what do we do with the economy such that the GDP is maximized, for example? And over here, it could be minimization, could be what do we do with your cancer rate so that your body, right? So your cancer rate is minimized. Okay. All right. So like I said, when you're trying to solve this, you can either have a simple problem or a difficult one. So our goal is to learn how to deal with difficult problems, right? Almost all functions are majority function are very difficult. And how do we deal with those difficult functions? Okay, well, to find a minimum, so we're going to use a simple example. So x squared looks like this. Obviously, this is an overly simplified problem, but the goal here is to look at a simplified problem, see how we solve it, and extend that idea to more complicated problems. So over here, all right, obviously the minimum solution at x is 0, right? You can see that, and we can even set the derivative x squared derivative, which is 2x, and equal to 0. Therefore x is equal to 0. So from this perspective, this is very, very simple problem. We know the solution. Now we're going to pretend that we don't know the solution, and this is something really complicated. And the way we can solve this problem to start off is simply to randomly start at a point. You're just going to assume 2, which we know 2 is not the optimal solution. But let's say we just assume we place a person here at 2. And by looking at the derivative, it will tell us whether we want to walk towards the right or we want to walk towards the left. In this particular case, you can visually see we want to walk towards the left. But in higher dimensional space where we cannot visualize, you would need to use the derivative information, right? So if we like the derivative basically will tell us which way to go. Now, if you go back to the first lecture, you'll remember that the derivative, if the derivative is positive, what does that mean? It means that if it's positive, it means that if we walk this way, the function is going up. And conversely, if we walk this way, the function is going down. So that's what that means. So if your current location is here, let's say I'm here right now, this is a now, adding a positive number will imply that I'm going towards the right. And adding a negative number will imply I'm going towards left, right? Negative, you'll go get smaller. Positive, you get larger. So therefore, if it's a positive, it means that if I walk towards the right, right, if I add a positive, the function is going to go up. Conversely, if it's I walk towards negative, walk towards the left, the function is going to go down. Okay. Since we're trying to do minimization, we're trying to walk the direction to go down. Okay. This means that we want to go, if it's positive, we want a negative value. Okay. Now, if I was standing over here, for example, if I was here, then it'll be opposite, right? If the derivative is negative, then I want a positive value. So here's the key relationship. If the derivative is positive, I want to add a negative value to walk towards the left. However, if the derivative is negative, I want to add a positive value to walk towards the right. This basically tells us by knowing the sign of the derivative, we know which way to walk. So basically, all we have to do is basically take wherever we're standing now and add the negative, the opposite of the derivative. And that will guarantee that we walk the opposite direction of the derivative. Okay. And that will get us our next location. So here, let's say that right now, the function is x squared, right? And therefore the derivative is 2x. So if I take right now my location plus the derivative at my current location, so my current location is 2, right? So here's 2. And the function is 2x, that's the derivative. And I plug 2 in because that's where I'm at. at the derivative at the current location, then the next location is -2. So I walked from 2 to -2. Okay. Now, now we definitely walk towards the right direction. We want to go this way, but it's obvious that we kind of went way too far. We want to stop here ideally, but not only do we need to know which way to go, we need to know how far we go. Okay? But it's very difficult to know how far we go. So normally what we do is we just, instead of walk too far, we multiply how far we walk by a small number, by a small multiply by a small number, which we call eta. So we don't just walk the full derivative. We take the derivative and walk a percentage of that. So like 20%. Okay. So now, if I had used eta, which is a multiplier, by 0. 0.2, then 2 minus the derivative times 0.2 give us 1.2. Notice how instead of now walk all the way to -2, it walked from here 2 to 1.2. So walk this distance. So if you just walk a little bit, you're probably going to be fine. You don't want to take a giant step. So that's what this eta, this symbol is called the eta symbol, and this is called also step size. This is the step size. So how big a step we take essentially. So if you take a big step versus a small step, and here if you take a small step like 0.1, 0.2, then it will guarantee that you walk here. Okay. Well, now that you're in the new location, you can do the same thing again, right? By looking at the derivative at this point, at this new point, you will know which way to walk, and you're going to walk this way. So if you did that, the first time will end up with 1.2. And then if 1.2 is the new location, you will walk again to 0.72. And then at 0.72, you will walk again to 0.43. So you can see that by taking smaller steps, you're incrementally approaching the minimum. And in the end, you're going to reach it. And this iterative solver is one of the most used and famous algorithm in machine learning, and it's called gradient descent. Okay, so we have a function, like picture this. We have a function, and we're trying to reach the maximum of the minimum of that function, like figuring out which input we put in to achieve the maximum minimum. And by using gradient descent, we can incrementally, like you can start any point here or here, right? You would little by little walk towards this final location. Okay, now that was one dimension. So you can imagine if we have 2 dimensions or even higher. Over here we have 2 dimensions. So this is the function where alpha and beta are the variables. So if I take alpha now, beta now as the current location, and then we take the derivative with respect to alpha, derivative with respect to beta, then this will give us the vector of the next location. Okay, so I want you to pause the video and essentially see if you can solve this, okay, to see if you can reach the next step. The solution is in the next page. Okay, pause the video because we're going to move on. Okay, here's the solution. Okay, so over here, that was the problem we just solved. Given this problem, right, then remember we were able to find a derivative. So this is the derivative. Like, take a second and see how this was the equivalent to a derivative of this with respect to alpha and beta. Now, typing this equation into Python is a pain. Instead, you always want to figure out a way to simplify it, so that into matrix vector multiplication. Notice how right here is alpha beta. Therefore, you can convert that into matrix, and alpha beta is equal to some kind of variable, minus 16 and 12. So this is equivalent to some kind of matrix, some kind of vector, minus some vector. So this is much easier to implement than this thing here. Okay, so let's say I define some kind of A, W, and C. So A, C, W, and eta. Eta is the step size. And the function was simply copy the function here. So I define the function. Now, if I'm trying to minimize this function, I have to run it in a loop. Notice I ran this in a loop. Basically, what I want to do is I want to calculate the derivative, AW minus C, right here. We want to calculate the derivative, and then we want to take a step. So the current W location, we're going to subtract the negative of the derivative, the opposite times some kind of step size. And we do this in the loop. So we take a step and another step and another step. And every single time we take a step, I show the current value of the function. So we're trying to go lower, lower, lower. So the current value at each step should go lower. Okay. So if I run this in a loop for 20 times, you notice how these are the steps, right? As we take each step, the current value of the function is going lower and lower and lower and lower, right? So this is telling you that you are essentially achieving the minimization. You're achieving the minimization of this function here. Okay, you're making this function go as low as possible, essentially. Okay, you want to take a second to really study. The key of this code is essentially the portion where we run gradient descent, where we find a derivative. Every time we find a derivative, we update the current location, and then we loop again. We find a derivative, we update the location, and we do that over and over again. Okay. All right. So for the exercise in this, this is it. So this is for part one exercise. I want you to do both these exercises. Now during class, for those of you who doesn't do the lectures ahead of time, you'll only have time to do this portion. But if you have the chance to do it at home, you definitely want to try this portion. Okay. This portion is really good practice. And try yourself. Like, see if you can follow basically this code and then apply this code to these two problems. Now, if you're really stuck, I have the code for you, but ideally you gain the ability to do this yourself, right? So by looking at this, you're able to write the code yourself over here. Okay, so that's it for the part one. Yeah, this is the part one of lecture on minimization. Okay, so in part two, we're going to then talk about regression. Regression, right here, regression. So okay, I will see you in the next lecture.